something classical. It's called classical heritage.
Right.
So I thought, well, how about geometric constructions? So what I'm going to do today is I'm going to walk through a bunch of the constructions and then talk a little bit about what I view as their importance, in our curriculum. Okay, so before I begin, constructions. Well, I'll begin with the constructions. We introduce these, say, late in the first semester after they've learned a lot of properties and done many, many proofs. So pretty much everything in here has already been proven in the first semester. Maybe they'll do 100, 120 proofs,
Wow.
that would underlie these principles. So then they get to construct it and kind of see that proof kind of come alive in a tactile experience. And I'll try to convey some of that as I go. Also, I don't have a smartboard, a touch screen. Normally I'd be up here, manipulating this digital compass and so forth, but I'll kind of have to do a slideshow for you today. It's also, the constructions is really like I put the kids in little groups and they help each other out. And that whole experience that they would have in the classroom, I'm not going to quite be able to convey, but we've got some of those things.
What year is this?
Well, this is going to be freshmen and some sophomores, and
Okay.
even some 8th graders. 8th grade would probably be doing this as well in the geometry. I haven't taught. I'd love to get back to it. I think it's been 7, 8 years since I've taught geometry. So anyway, I'm just going to walk you through. Now the first couple, I'm actually going to do the construction. And so what we're going to do is we're going to construct a segment called PQ. That's the sum of AB and CD. So first thing is a compass. It's very interesting because all it can do is, well, we think of it as making circles, of course, spinning around and making a circle. But it really is just a measure of a particular length, right? And something I should point out is the Greeks didn't believe in rulers, like partitioned rulers. So they wanted things to be very pure. And a compass is wonderful that way. There's no partitions or anything. You just take one existing length and then reproduce that existing length. So I think that's pretty interesting. All right, so anyway, we're going to go ahead and construct a segment. This would be the very first thing they do, probably this very problem, in fact. So they pick up their compass and, well, first they practice making circles and things because they just have to get a feel for how to use a compass. And okay, so let's go ahead and do it. So they got to come over here. As I'm sure you all know, we got to come over here and measure AB. All right, we have to shrink that down. We make that measurement and we go ahead and reproduce that down here and swing it. And we talk about in the class how to make that arc a good size, readable but not enormous. And this is actually even just this little move with their little, paper or their handheld compass that has a pencil on it is something that they have to get used to. And they all, luckily, pretty much know what to do, with a problem like this, is to, go ahead and take this. But then they'll come down here and they'll do this, right? Big mistake. They have to add it, right? So this is just part of that learning experience. Is like, in a physical way, what does addition, really, really mean? Like according to the number line and so forth. So here's just a property where, they can internalize abstract ideas through pictures. And then there's our segment. I'm not going to take the time. There's P and Q over there, and they would label that stuff. So there's some, then we can add and subtract, and of course subtracting, we'll have that in a problem set, and they'll go the other direction and do some things. Okay, let's go on to an angle. Okay, so an angle is pretty weird because, remember, a compass can only take existing lengths and measure them. So I'll just throw this problem out at them, or that's how I used to do it. And I'll tell them, yeah, just start with line. Okay, what are you going to do now? We're going to make angle 2 equal to angle E, and here's what they tend to do. And okay, I got it. Whoops, sorry about that. I was worried that this would happen. I got to go here. So flip this, turn it around, make it all work. So they're going to come over here. Is their natural tendency, and they're going to measure this length. But of course, this isn't actually a segment. This is a ray. But they treat it like a segment. I just let them go with it. Fine. And they come down. Whoops. They come down here and they do this, and they mark it off. Okay, that's all wonderful and good. And just let them do their thing. They come over here, and again, this is a ray, so it doesn't have a set length, but they treat it like a segment that has a set length. And then, well, now they have a problem. Like, So some of them draw another line, but they're guessing, so we have to talk about that. They'll just sort of eyeball it up or something, or they want to dig out their protractor, and they'll do this. Can't do that. We don't actually know where that line goes. So they got to futz around with it. Whoops, undo that. But then they understand. This is all fun discussion, actually. So they're experimenting and investigating. And we're not in a hurry here. You know, we want to just take our time with this lesson, especially early on. So if they don't understand, let's tell them to just swing it up in space and just, maybe you'll get lucky, right? Maybe you'll just get lucky with it. And then, they get it then. So then they come up over here, and they then say, well, why don't I go ahead and measure this right here? So they're measuring that length, because they treated these as segments, and then they realize, so they have these wonderful, like, concurrent points, intersecting lines, all these just neat things that they haven't really experienced before, coming through, and then they put down their ruler, and they go ahead and they draw that. Well, they tend to go here, because again, they're treating a ray like a segment. We have to talk about that. We get to this spot. And it's sort of like, boy, it looks like the same thing, but how do we actually know this is in fact the correct angle? And so a few kids might know, but it truly, not all of them will originally, so I'll talk, okay, so we have this segment and this segment, so I'm marking these in blue. Can you see that okay? Yeah, so those are congruent. And we have, say, this segment here. Again, you treated a ray like a segment, but it's not the end of the world, and those are congruent there. And pick another color, and then you constructed this to match this. And so you have, and of course they've done all these triangle proofs. So you have side, side, side triangle congruency that we all learn about. And then the wonderful thing called CPCTC, right? So we know if two triangles are congruent, because all three sides are the same. And we do this earlier. I give them pieces of spaghetti, 3 little pieces, and say, try to build 2 distinctly different triangles. And no matter the way they orient it, it's the same darn triangle, right? So there's no way around it. And then, of course, if the triangles are congruent, then the corresponding parts, specifically this angle and this angle, have to be the same. So we support that side, side, side congruency and the corresponding parts theory. Now then I tell them that this is not the most efficient way to do it, and the best way to do it, of course, and I'll show you real quick. And this will be the last of the live constructions I do. Then we'll just go to slides, or this thing will take forever. Is they can just come right through here and just make an arc through like that, and then here, like that, and then come up here and measure that. Oops, there we go, right here. And so doing this with a mouse is a little bit slow, but that's okay. And then they measure that and that. Whoop, darn it. Yeah, pull it on over. It's pretty good, pretty good. And there we have it, right? And that's actually not a bad thing on the same picture, because it confirms, like, 2 different ways to accomplish the same task, still the same angle, all of that good stuff. All right, so we see all sorts of, I think, to this point, benefits of doing these constructions. And also just the ability to do this stuff manipulatively with your hands. Everything in math, right, it's so abstract, symbols and, this unknown X and all these sorts of things. So to actually be able to pick up, and even in geometry, if they're drawing something, it's still just a pencil and ruler, and we have to pretend that the triangle is perfect, but it's constructed from these basic parts, and I think really useful. Okay, so now where's my other? There it is. And I'm just going to buzz through and show you a few more, but I'm going to do it this way. All right, I'll let you think about it a little bit here. So after they do an angle, well, why don't we see if we can make a new angle? I'm sorry the slides are a little small, but in order to be able to fit the construction in, I had to go with this size. So we're going to make a new angle U, okay, and we're going to take F and then subtract E twice from it. So think about that for a sec. What are you going to do? Come on, oops, wrong button. There we go. So we're going to start with a line. And now the kids won't know this initially, so I explain. Well, why don't we actually start with F. I started in this one with E. But if we strategically make these arcs the exact same radius size, we can then throw it down there. And this is very beneficial to do that, okay? And I'm sure you all know what to do now. You're thinking about it. Okay, the kids, of course, would be doing this. Right, we need to measure F, right? And that's difficult for them. They want to put the compass, say, from here to here. Some students, they didn't quite yet grasp that we're taking that distance across. So that's actually a chord property of a circle, and all of this is going to relate. Later, we mark that off. So there is angle F, of course, duplicated. But I actually don't like them drawing that line. Oops, there we go. I like to just leave it blank, and then we go to, and we subtract E. And there's that subtraction idea, going back inward, right? Right. So just a neat way to think about it, nice spatial reasoning, you know, and then they finish that off. And they get to, they're doing all of this stuff, which is pretty neat. Anybody have a question? All right, so we just keep expanding. So this would be like day 2, so day 3. So they have all these properties of perpendicular lines that they've already talked about, done all sorts of proofs on perpendiculars. And okay, so we have this segment, and we can construct what's called the perpendicular bisector, as you can imagine, perpendicular to this existing line and passing through the midpoint of the line, the segment, excuse me. So how do we do it? Again, I just actually throw it at them and let them see let's see what sticks to begin with, because that's what they enjoy doing. Just, you know, give them a bunch of paper and try it again and again for a few minutes. So we have to measure more than half, so they eyeball that, swing an arc out into space. There, so we have equidistant distances from each endpoint. Oh, right. And here's what they do. They grab their ruler then, and they do this. They bring it on over here, and they draw the line right there, right? And do you see what the error is? You may or may not. See, although we talk a lot about a line being defined by 2 points, this really hammers home the idea. So they're just guessing here. You know, it looks perpendicular. So there's a difference between something looking a particular way and then being valid. So this is a nice opportunity to talk about mathematical validity. And of course, all I have to do is, well, how did you know to put your ruler that particular way? And of course, they took the little lines on the ruler and made them match up, you know, with the segment. That's not valid. So they have to, of course, get rid of that ruler and finish it off and make a second set of equidistant points to define that line. So we get to talk about those properties right there. Okay, so they're kind of mystified by this one. Even though they've done proofs of it, they're mystified, and maybe you're mystified by it too. I mean, that seems pretty neat. It sort of like works. It somehow intuitively it makes sense, but like, why does it actually work? So what did we do? We constructed a set of intersecting arcs, so in red, another set, and those are different lengths. And then, of course, there's this segment through the middle, and so we produce these 2 triangles. Again, that side triangle congruency, red, green, and black. And so if 2 triangles are congruent, what's true? The corresponding angles are congruent, right there, okay. Now, what's the goal here again? We're trying to explain how we know with certainty that what we just constructed is a perpendicular bisector, okay? And now here, they've written up this proof maybe a month ago. At this point, we're not going to write it up. We're just going to talk about it like I am with you, because or else we don't want to get bogged down. So now we have a smaller triangle that's congruent now by another reason, good old side angle side there, with the reflexive property, right, that shared side in black dashed. And well, now we have 2 sets of corresponding pieces. The blue marked with the 3s, and of course the 2 congruent angles. And another property, right, if 2 angles form a straight line and they're congruent, they have to be right angles. So there we have our perpendicular bisector. So go ahead.
So Dave, when you talk about having done all the proofs earlier,
yep.
Did they do proofs without images, without pictures? Are they just...
They would have, for the most part, would be given a pre-made picture that's set up with, you know, some what are called givens, and then with the conclusion they have to draw. Okay. And they would mark that up, but they're just using a pencil and doing some markings. Okay. And I've tried proofs all sorts of different ways. I spent a few years doing essay proofs, which would be a more pure form of a proof, but it was too hard for the students and really kind of overwhelming for me to grade, because you have to read. That's an interesting thing about constructions, and one of the reasons we still can do it, and other schools it's a real challenge, is our class sizes are small. I have to collect all these papers, the geometry teacher, and read them all, because it's a story in it. It's not just, oh, I got the correct answer of 16, okay, it must be right, you probably did it. I have to read the proof, the teacher has to read it, and if you have classes of 30, 4 sections of 30, take home 120 papers and read all those darn things, That's just, it's too much. So we can keep doing that because it's not so, it's a lot of work, I'll admit, but it's not overwhelming. So there's our perpendicular bisector, that's fun, but then the question is, a shortcut to the whole thing, okay? Why don't we just make everything the same? Sort of like when we did it with the angle, this is the really quick way, so why not go ahead and tell them that's worthwhile. Okay, and also, of course, we have a midpoint, so I make sure to emphasize that a perpendicular bisector is also the same construction of a midpoint of a segment. But what if our line didn't have endpoints, and there was just some point on it somewhere, and we need a perpendicular, of course it'll be here, right there. How are we gonna do that? Gosh, they want to use those arrows as like endpoints of a segment, but they're not. So if we go back, we'll just go back a little bit, right here, there we go. So we're looking at equidistant, that's a key characteristic, all these equidistants. Boy, that one should be it. Maybe it's a giveaway for you, you know what to do. Okay, we have to, come on now, there we go. Right, we have to, come on, produce equidistance. So we force that point to be equidistant from some arbitrarily determined endpoints, and any size will work. And now we have our segment, and so we can just use the construction that we just had. And now they can lay their ruler down, right? Because they're the given point. So we get to talk about, yeah, it was a given, it's a given point, and there we go. So it can be constructed. So we get to see, in action. Of course, they see this all the time in mathematics, one thing build on the other, but I think it's more satisfying in constructions, because you're playing around with this compass and making this actually very aesthetically pleasing. You'll see some of them, they're quite nice, I think. Okay, so then the next perpendicular, so this would all be one day's lesson right here. Let's go to this. Let's say that point isn't on the line, it's just up in space somewhere. What are we gonna do? They want to just put the ruler down and draw it, right? Oh, I did it. No. So we have to produce equidistance. Again, a key characteristic of perpendicular. So there. So that arc produces two equidistance. Of course, the intersection point on the right, sort of, and on the left. And then at this, they all know what to do there. Yeah, let's do that. And of course, there we go. So now they have three types of perpendiculars, which can build altitudes, all sorts of perpendiculars, rectangles, squares, all this neat stuff can be built. And so these things will be assigned.
Do they go like, oh?
Oh, yes. They have a lot of fun with this.
Yeah.
And the pacing has to be right. It's hard. Fine motor skills, kids have a different array of fine motor skills. So just like in any teaching, you have to find that medium spot, right? So to keep the kids who already have it moving forward, and kids who it's a little more challenging, in there enough where they're understanding the concepts. Good question. Okay, so now just a couple of little, there's many constructions, but let's say if we can construct a triangle with some pieces, okay, and particularly we have to make a right triangle. Okay, so they'd start with that. And they'd, of course, as you can imagine, mark off the length of C to D. They all know how to make, I'm going to make the right angle first, right? So this is the fun. They get to use their one, and they have to know which type, right? It's not always obvious to them. So there is our little method for constructing a perpendicular, which of course is a right angle. And then they go ahead and duplicate angle C, which at this point is very easy for them. It's old hat, no big deal. But this is, a lot of times they don't extend these far enough. They're up here and they're like, well, I don't know what to do. Right? Well, you just keep going with it, because these are lines and arrays, so that you just keep going until they intersect. You're fine. So these ideas that we think are obvious are not obvious to them, and doing all of this helps them to just grow intellectually. Let's see here's a challenge problem for us. So what we see is I'm giving angle D, but I'm not giving angle R, and I'm not saying what size angle R, and I'm actually giving angle T, which is going to be that angle up in space. So how in the heck are we going to do this in a valid way? All right, I'll pause in a moment. So, you know, clearly we're going to make angle D and mark off D to R. So I went ahead and did that. I think I did. There it is. So they're at this spot, right? And they want to build T at R, but they can't, because or else I call it R, right? And they want to go up here, and like, you can imagine what they do is they like put a dot down, construct T, and hope it goes through R, but that's not valid, is it? So they're playing around with it. And again, you got to measure how much time is the appropriate time. Give them enough time to futz with it and screw it up. And you always hope a few got it, and then you can call on those students. Well, why don't you explain to the class how you do it? And so Ben would explain to the class, well, what you do is you take that arc from D. I don't have it in, but you're going to take that arc because it makes it easier. And you're going to swing out. You see what's going to happen now? Okay. So we go up, and there's our arc on D, or on T, excuse me. We measure T. There it is. And measure D, right? Because of course we know that the three angles of a triangle add up to 180, and so if we know two of them, we automatically know the third, right? We also have supplementary angle idea going on here, so we construct the supplement of angle R, thus producing it. So just a kind of a fairly simple but still nice application problem that makes them think. It's not just automatic reproduction of obvious things. And there's many constructions that are like this. We have pages full of neat things for them to do. Okay. Good, okay. Go ahead.
Can you always read the question? My eyes
Oh, I got you.
Okay.
Bisect a 180-degree angle.
Bisect 100, okay.
Yeah, bisect a 180-degree. And by the way, I can turn all this into a PDF and share it all and all that stuff. Right, because we're going to learn how to construct an angle bisector, so let's start with this. And they all know what to do, actually, because they know that a 180-degree angle is just a line, so they make a perpendicular line, like we've already learned how to do. So then, what if it's just an obtuse angle? Okay, well, you know, what's the difference between 180 and 179? Not a whole heck of a lot, right? So why don't we just do the same old thing, right? There we go, we've bisected that. So then the question is, well, can't we don't bisect any angle? What's the difference between 179 and 178? Or 50 degrees, say. And of course, there it is, right there. And we draw that. And do I have, no I don't. But just once again, just to reinforce what's underlying all of this, of course we have congruencies here, equidistance, so congruencies here, and we have the shared now bisector there, and we can easily prove that. And we probably would discuss it a little bit in class. So now they can bisect angles. Okay, so now that we can bisect angles, have some fun, we can construct some specific angles. How are we going to construct this? Exactly 60-degree angle. I'm giving us nothing, just some instructions. Construct a 60-degree angle. Of course, an equilateral triangle, right? So we make an R. It's very simple. All we have to do is that, right? And embedded, I don't think I have it, but embedded in this, right? Because all these distances are equal. So equilateral triangle. So again, characteristics from things from earlier this year.
Oh, 60, 60, 60.
Yes, yeah, 60, 60, 60.
Okay.
Now, 45, I'm going to do it a different way. You know, students would say, well, now that we know how to bisect, we bisected one of those 90s that we made. But this is more fun right here. Is why not? Well, okay, I guess I did have that. We can just bisect, and what do we have? Of course, a 30, right?
Bisected again, that's 15.
Right, and this is not obvious to all of them. They might want to do something separate over there, and they like mush them together or whatever, but of course what you all see is, and this, again, it's so interesting how they really have to think through this. It doesn't jump out at them, and then we get a nice 45 there. And it looks nice too, I think. And their papers, many of them they look fabulous. They're very satisfied with how they look. Okay, so we can do all that neat stuff. What's that? I'm supposed to, let's see, what else do I have here? Yeah, these are built, they're not just observing, hands-on, super fun for the kids to be, immersed in it. Oh, yeah, a ton of accuracy and precision are needed here. Can't just sloppily do things. And of course. Andrea, yes.
A student of yours?
Yeah. Yeah, one of my stars from back in the day, for sure. But, they might be a little sloppy in their day-to-day work, but when they get to construction, they have to be neat about it. And I think they want to be. Parallels. Keep rolling. What do we add here? So I've been going for about a half.
You're good. Keep going.
9?
It's 9.
Okay, all right. There's many ways to do parallels. We actually go through numerous. I'm just going to do one variation. This is an interesting idea to them. We can just draw a random line through the point like that at any angle. This random line that I have in blue is, of course, going to be the transversal. And so, they've proven all of this, these ideas, but that would have been, again, probably a few weeks ago. You see what we're doing, we're going to make corresponding angles here. This is not an obvious thing to them, but then they're, oh yeah, I can do that. The way they want to do it is they want to raise a perpendicular and then a perpendicular to the perpendicular. That ends up being their favorite, but they like doing this too. So corresponding angles supported there, all that neat stuff. I don't think I'm going to actually run through the constructions, but just to show you, then we have a whole array of parallelograms that we can give them. Oh, I guess I do have this one. Okay, we get to see that. Okay, maybe I went too fast. So they have to know the properties of the parallelogram because the naming of a quadrilateral or any polygon has to go in order. It doesn't zigzag. So L, A, S is out here somewhere, and T is over there. And they have to realize, oh, I've given A, S, how am I going to make that work? And they have to know. So that's, of course, how they start, but they'd have to know that the opposite sides of a parallelogram are congruent. So if I give AS, I'm also giving LT at the same time. I don't know what that is. Uh-oh. Huh, let's get rid of that. Let's just see if I'll just advance it with this, and then maybe it'll be fine. Okay, there's T. And they have to construct a parallel, right? So how are we going to do that? There's no way around it, so we're going to go with corresponding angles. Of course, what I'm doing is duplicating angle L. And then there's that wonderful parallel. And then they have many options for finishing it off. All right. A length intersecting on already existing line. We've seen that. But it still can be troublesome for them. All this equidistancing and intersection idea, it takes some growth. We get a pretty nice looking parallelogram. Okay, let's see. A rhombus, neat rhombus things to do. I don't think I have this one. Constructing rect, just giving you just a little bit of a sample of things. This would be homework. A lot of it we do in class though, because the correcting can become overwhelming. So as they're going and they'll work with a partner, another person, they each have to do their own construction. But I can walk around and correct it right in the moment, so then I don't take home 2 hours worth of review. Maybe it's down to an hour or something, and they can move on to the next thing. So we're done with constructions for a while, and we just go back to regular old math, and we talk about more things, and they learn a bunch of stuff about circles. So we have a unit on circles, and then we come back to constructions for maybe 2 days. After they've, learned, solved circle things, how many angles, inscribed angle, etc., etc. And then done a few proofs. So this would have been proven. Let's see. Construct the circle that's, do you remember this one?
Oh, read it to me, please.
Okay, construct the circle that circumscribes the given triangle. Okay, so circumscribe, so it has to go around. Okay, so what we're going to do here, and they would have learned this. Yeah, this is where it gets harder. But okay, we're perpendicular bisecting that horizontal segment there. So there it is in red. We are perpendicular bisecting that oblique line on the left. And there it is. And then, oh, it's so much fun. What happens if we perpendicular bisect that third side? I wonder. So curious to know. I explained to them that they can have their compass open really wide. Like, get it out of the way and make it look really nice. And there we go, perpendicular bisect. And lo and behold, isn't that something? They all concur, right? Points of concurrency. There it is. Anyone know the name of that? What's called the circumcenter. And we're gonna, you know what we're gonna do? We're gonna lay down our compass and, oh, fabulous, huh? This is great for those of you who want, you know, do a little home construction or something like that. Right? Kind of useful maybe. How did that happen? How does this thing work? Right? It's just, it's so cool. And it could be any triangle, of course. It's more fun with an obtuse triangle. Well, what did we do? We constructed the first perpendicular bisector in red, so that center point has to be equidistant from the endpoints of the first segment. The green one, same idea, it has to be equidistant because that's a perpendicular bisector. And the light blue one, same deal. That lies on a perpendicular bisector of that. And so we have a syllogism here, essentially, right? If one thing is congruent to another is congruent to another, they're all congruent. So we have the definition of a circle. You know, all points equidistant from a given point. So that's fun. Okay. Is there a question?
So don't they just want to make the circle without doing that?
Oh, they do. This one's an easier one. I don't have a slide of the inscribed circle because it's, I don't know, we'll maybe get bogged down in our discussion, but that is one where they cheat the construction a lot for various reasons. In this one, I'll backtrack here. I'll just do this. They really can't. Like,
Oh yeah, there
yeah,
is
they don't
no-
know where the center is.
Yeah, you're
Yeah,
right.
so the center has to be determined. Now, what's really fun, and I hope I have a slide of this, I don't remember exactly, is what if we reverse it? What if we have, oh yeah, I do, I'm sure I do. Let's see, yeah, there we go. Let's reverse this thing. Okay, so we had a triangle, and we were able to find this point and then make the circle. What if we have the circle first?
Oh gee. Do we know what kind of triangle we want?
Well, we don't care. So the key again is that this whole equidistant thing, what did we just construct? We had we treated the triangle as really just segments with perpendicular bisectors. So we're going to have to use that characteristic there. So does it really matter, Ms. Pryor, what kind of triangle? Of course not.
Oh.
Just go ahead and draw, oops, I went too fast. Just go ahead and draw yourself any old side of any old triangle.
Okay.
And there we go, and then here's the other side, and you actually don't even need the third side because we've already determined the center there. So again, kind of neat application that a person could really do in their own, you know, home remodeling project or something. Got to find the center of a circle, and you know, get the old jigsaw or whatever going, kind of thing. Okay. So yeah, it's fun to just do that, and you get to manipulate it. It looks so nice. Okay, now I would say all geometry classes get this far at Brookfield Academy. Again, with many more problem sets and applications. And then depending year to year, we may get to this. And this is, here I didn't go as in depth maybe with my slides because I wasn't sure how far I would get today. But trisecting. So we're done with circles, and we have another unit on proportionality. You know, similar triangles, A is to B, is C is to D, and all of this sort of thing. And they all know how to bisect. Actually, that's how I would open this. Can you bisect this segment? They all just make their perpendicular bisect. How do you trisect it? And of course, they bisect the bisect. Well, no, that's dividing into quarters.
Yeah.
Yeah, so then they want to bisect again and again. And then we get into some calculus ideas, right? What if we bisect it forever, partition it? I guess eventually you'll get it trisected. But how can we do it right from the beginning? This isn't going to be obvious to even I haven't taught this in many years, and I had to think about it for a while. How do I want to do this? So here's this random line thing again. It could be any line, and what we're going to do is we're going to divide this second line into 3 parts. Any distance is fine. We're going to connect the third one And then we're going to produce corresponding angles, which produces parallels. And now we have three similar triangles, the small one, the medium one, and the large one. And there's all these neat properties that are all done in advance. You know, you give them like some numbers with x's and y's, and they have to solve for, you know, certain lengths. And we also prove it, but of course, these sides are they're not congruent. I wish I had made this a little different, a little longer, but they are in proportion. So since these three are equal, these are, so we can divide it now into any number of pieces that we would need using these parallel lines. So right, we see all these pieces coming together that's satisfying total spiral, constantly spiraling in these constructions. Let's see, another? Got maybe one or two more. Oh, again, this isn't going to be every year, but in certain years, or maybe this is a place where we could differentiate a little bit, give some extra credit, or something like that. You can actually construct like squares of values, and I'm going to construct a square root. This would be near our final unit. This would also be in our unit with similar triangles. And as I go through this when I'm done, I'll explain to you how the similarity is underlying this construction. I'll do my best with it.
Can you read it to my wife?
Yeah.
It says, use the segments of unit length, length A, and length B to construct segments of length W, X, Y, and Z. So what I'm going to do is I'm going to take these two, and I actually, do you have a meter stick? Or a ruler? Because we might actually compute, make sure my construction is valid, or whatever.
I don't know that I do.
Okay, that's
sorry.
okay, that's okay. So how are we going to construct a square root of a product? Oh, such good stuff. Okay, now I really do, I have to walk them through this like I am.
Good.
This isn't one that maybe one or two students would be able to come up with this on their own. So A and B, and honestly, I probably didn't come up with this originally on my own. I read it somewhere. Okay, so we'll measure that off. There's length A plus B. Boy, how are we going to make a square root of the product? How do we even multiply? That's another thing. Like we learned in an earlier one how to multiply. But again, I just wasn't sure how long this would go, so I didn't include that one. Just went right to the good stuff. So we're going to construct the perpendicular bisector of that sum. And what I teach the kids is if we only need a midpoint, we put our ruler down and just make a little segment there to represent our midpoint. So we have the midpoint of AB, okay? And then we are going to, why would we do this? Why? Make a semicircle. Huh. Okay.
Isn't that something?
And then we're going to take that point, you see it in the like light blue at A, and we are going to raise a perpendicular at A, or at that dot. Okay, there's my ruler, draw that line, and that line is exactly the square root of the product of A and B. So if...
Oh, come on.
Are you sure?
Yeah, I'm sure I'll prove it to you.
Okay.
So Z, so that's Z. And here's the proof. There's a lot here. There's a lot embedded in this. And this is where, you know, geometry gets better and better. Okay. Let me look at my next slide here real quick. Let me see what we have. So there's a proportion, yeah. Now that proportion, that all would have been taught for sure, just not this construction here. And then of course, okay, we don't have that, I gotta go back. So there is a property, and they learn all of this in their circle unit. If we have a circle, particularly a semicircle, an angle what's called inscribed is going to be, that's going to be a 90-degree angle guaranteed. All angles inscribed in a circle, their measure is half the measure of what we call the intercepted arc. So specifically for a semicircle, we have a 90. That was the key. That's why we needed a midpoint to produce our semicircle to be able to get a right angle there. And of course, this was constructed as a right angle. So we have the large right triangle, this little right triangle here, and this one here. And I'm not gonna run through the proof, but all three are similar to each other. You could imagine picking up this small one on the left, turning it 90 degrees to the right, kind of placing it on top of the one to the right. It's smaller, but it's the exact same thing. And so what we have is this length on the small triangle corresponds with this length on this triangle to the right. And of course, this longer leg on this right triangle to the left corresponds to that leg on that. And therefore, of course, we cross multiply, so we get to do a little bit of basic algebra. So z times z equals a times b, and so z is the square root of ab.
Just briefly go back and tell me how you got the blue dot where it is.
The blue dot, here I'll just zip, zip, zip. The blue dot actually came from the very first step of building A and B. Because I knew the whole
It
time.
seems like you just pumped it down there.
Yeah, it was there the whole time. Right, so this one construction would probably be, it might be a full class period. If we, you know, and then we have to decide as a teacher, is this worthwhile or should we? Because how many students am I going to be able to capture with this? It might look neat, but are they really going to understand it? So this probably is an expansion problem for the interested students.
It's the original distance of like A from above.
Yeah.
A from above.
Yeah.
Given in the problem
Yeah,
up above,
yeah.
he just measured the distance of A and marked that line originally.
I think I have one or two more. Yeah, we're about there anyway. So let's, what the heck? At least this one. This one, I don't know. We do some other circle ones. Construct a line tangent to the circle through the. What they want to do, of course, is they want to lay down their ruler
I'm sure Barb got this.
and just like have it bump up against the circle to make their tangent, which they can't do. Here we get to talk about validity again. So if I may, grab that little ruler. Which way do we turn? Come on. There we go. Right, they wanted. Yeah, this is going to be a little. They want to do something like that, right? That's not a valid construction because this is not a defined point yet. So we talk about that. Yeah. Yeah, I did it. That was so easy, Mr. Reiner. Well, let's get rid of this. So we have to make it valid. So we'll make this our last one of the day. Although I do have, well, I got a couple more. How are we going to do it? So we get to use the same principle as just a moment ago, actually. So we're going to connect. We're going to bisect. We bisect really to get a midpoint. I shouldn't have drawn the whole thing there. And we're going to get this semicircle right there. And you see how the semicircle intersects the circle. So that point is now defined. And it still seems magical, I suppose, doesn't it? Like, yeah, that's it. And what's going on here is, and again, I'm going a little quickly here for you, but we just spoke a moment ago about in a semicircle, right here's the diameter, so an angle inscribed in a semicircle has to be a right angle, has to measure 90 degrees, and we made it specifically so it would land right at this spot on the original circle. And a key characteristic that we talk about, of course, in class is that a tangent line is always perpendicular to its intersected radius. So we can construct a...
That's the definition of a tangent, perpendicular to.
No, it's actually, the definition of a tangent would be a line that intersects a circle in exactly at one point. So this then would be an attribute, a characteristic, a property of it. That would be, again, at this point we're probably not actually writing proofs, but we talk about it like we are now. Because there's only so many proofs you can write until there's mutiny.
Avoid mutiny.
Yeah. And the last one, what the heck here, we'll see if this is another one I really jumped into. Okay, what we're going to do here for that very last construction, so we did a bunch of Pythagorean theorem stuff, and we might do a couple of basic Pythagorean theorem constructions. This might be one I do with the class. We're going to construct a new square, C, that's exactly equal to the area of A plus B. And I think this one is probably going to be pretty easy for us all to understand. So we're going to measure A down here, there it is. Of course, I already have a perpendicular set up down below. We're going to measure B right there. Of course, connect. There's our wonderful right triangle. I wish I had cut it off, stopped it here and here, because there's our hypotenuse of our right triangle. And we all know our Pythagorean theorem, right? A squared plus B squared equals C squared. Now A, here's A, so A squared would be lying down here. B squared, we could actually construct the square if we wanted. They get to see how the Pythagorean, so we're going to build a perpendicular. We're going to take that hypotenuse, mark it off. And then just, because a square has equidistant sides, so very easy. And then there we go, right? And I promise you that, although it doesn't look that much bigger, yeah, that, if we measured that, and I did it at home, I got a ruler, put it right on my computer screen, pulled out the old calculator, because we got decimals and all that, but yeah, it's remarkably close that this area is truly the sum of these two areas. Yeah.
That's great.
So it kind of is a neat way to really internalize the Pythagorean theorem. See that, and use all of our, and I think, yeah, that's the last slide. That's all I have for you today on that. So,
Your students applaud after each class.